Okay, so then when we have to think about collusion, collusion would mean that the firms are basically going to cooperate with one another. The result that we should be expecting is that the firms will produce less in an attempt to capture more profit. Okay, so if we use that same set of numbers that we had before, so now I still have my 30 minus Q, which is my inverse demand curve, and I have my Q, right, which is basically the Q1 and Q2. I'm going to still have my, in this case here, my marginal revenue now, right? If I'm trying to solve this, this Q is the big Q. That would mean then that if I take the first derivative of this 30Q minus Q2 minus Q squared, that would be 30 minus 2Q. They're basically going to equally split the market. And in this case here, they're each going to produce 15, right? That would allow these firms, as colluding firms, right? I'm sorry, that the market Q is 15, and they're basically going to split that market equally and each produce 7.5 units. We needed it to be less than 10, which is what it was previously. So again, the way that we solve this is we actually just solve for the big Q, and then we just divide it in half, because they're going to equally split the market, as long as they're equally powerful. In this case here, then the Q1 would have to equal to Q2. They both face the same marginal cost, and you would have 7.5. Look at that, what that does then. If we look at this on the picture then, 15, 15 is where the collusion curve starts. So notice what's happening here. This is the competitive, this is a very important slide. Here is my competitive equilibrium, way out here, right? And then we slowly bring it inwards, right, for the Cournot-Nash equilibrium. And then we can get the collusion equilibrium here. Now, what about firms that do not decide simultaneously? What if one firm makes a decision first and then the other firm makes a decision? In this case, let's look at the first mover advantage, what's called the Stackelberg model. So one firm decides to do one thing and then the other firm reacts. Okay, so one firm is going to set its output first. To make life simple, we're going to keep our same function here. Marginal cost is 0, marginal market demand curve being the same, 30 minus Q. Okay, so firm 1 is going to, it's going to think about what firm would do. But firm 2, which is not going to be our first mover here, is going to take firm 1 output as fixed. And it's simply going to plug whatever firm 1 decides into the into its reaction function. Okay, so for firm 1, we know that it's MR, which is, it has to be equal to MC to find profit maximizing output. Well, we know that the MC is equal to 0, so we know we need the MR to be equal to 0. Revenue for firm 1, this is our reaction function that we had solved. Sorry about that. This is the reaction function that we had solved for before. Our 30, right, I just distributed out my inverse demand curve to my Q1, right? So I just took my 30 minus Q, big Q, times Q1. And I got my firm 1's reaction function. Now what we do is we see that firm 1 now is going to produce 15, but now we need to substitute that 15 in for Q1 into firm 2's reaction function. What we find is that firm 2 will only produce 7.5. Interesting, right? Because what that basically means in the Stackelberg model, the first firm actually gains an advantage. Firm 1 is going to produce twice as much as firm 2. Its profit is going to be twice as large. And it's basically going to get that because it gets to make the first decision. Now, that's a little bit unusual to be in a Stackelberg model. What happens much more often is what's called the Bertrand model. And in the Bertrand model, each firm is going to, in this case, they're going to compete right, in this case on the basis of price rather than output. And in this case here, the price is going to be considered, fixed, and they're going to determine their prices simultaneously. So let's keep the same kind of functions we had before. 30 minus Q being our inverse demand curve. Marginal costs, let's keep them the same, but this time we're going to make it a positive number, 3. And, well, we could just quickly solve the Cournot equilibrium, and that would be 9. Our market price would then have to be 12. Each firm would have a profit of $81. But let's then actually try to determine what the price is going to be, right? Because that's really what the Bertrand model is all about. In this case here, the Nash equilibrium it's going to be the competitive output. It's going to be the Nash equilibrium with respect to the price. The price is going to have to equal the marginal cost. That would mean that the price for each of them would have to equal 3. Now, if the price is 3, right, and they're charging the same price, they want to charge a price that's as close to perfectly competitive as possible, then the firms total are going to produce 13.5. The firms will earn 0 profit. They can't charge anything more because then they wouldn't sell anything. They can't charge less because then they would actually lose money. The reason why this is important is because the Bertrand model, as compared to the Stackelberg model, shows how important it is to think about what variable it is you're looking at. Are you looking at price or are you looking at quantity? Right? In the Stackelberg model, I'm looking at output. In the Bertrand model, I'm looking at price. Now, it's not often the case that firms are producing a homogeneous good. Sometimes it happens, like in the case of the airlines, but more often than not, it doesn't. So the Bertrand model actually applies much more to the airlines than anything at all. Okay. Now, we could also look at this in terms of a differentiated product. What if there's a difference in design, performance, durability? So this would be something more along the lines of the car model here. Okay, so if that's the case, right, then let's say they have fixed costs of 20, no variable costs. Let's say they face the exact same demand curve. In this case, let's make it 12 minus 2P1 plus P2. And, right, obviously, as they sell more, the only way they could do that is by lowering the price. If the competitor is charging an even higher price, then obviously that firm will gain a competitive advantage. And when that happens, what the firms are going to do is they're going to set their prices now. We're going to presume that they set them at the exact same time. That would mean that what we need to do is we need to find the maximum profit. To do that, we need to find the revenue here minus the costs. That would be P1Q1, that would be the revenue, minus the $20 fixed cost. Now we need to distribute out, I know what my Q1 is, right? That is my, that was solved for right here, Q1. And multiply that by P1. And distribute it out. And then if P2 then is fixed, then what I do is I solve for each of the firm's reaction functions, right? Because then I substitute in for P2, right? Solving for P2, I get 3 plus 1/4 P1. Solving for P1, I get 3 plus 1/4 P2. Now, what if these firms collude on the basis of price? Then they're going to collude such that they both earn higher profits. In this case here, they're going to charge more, in this case $6, and they're going to earn a profit of $16. The reaction functions look like the following. Now the functions here are P1 and P2. The reaction functions give us the equilibriums of 4 and 4. That would be for the Nash equilibrium, but the collusion again, they both are going to charge higher prices and produce smaller amounts. Okay, I'm going to stop the video here, and I might be able to do the rest of the slides in one more recording.